All right, let's get started. So I pushed some to the repo today. So if you don't see the code that I'm talking about today, you can pull and get that code. So I used to have this jumper no physics code, which I guess I still have, in the examples repo. And this is a game that I made to use as an example in this class that I call Jumper because I'm not creative enough to come up with a more creative name. This Jumper no physics, it's the core of the game and it has all the stuff that we'll talk about today, but it doesn't have a physics engine in it. The physics engine is just an empty method, which isn't very interesting, can't play the game or anything. I didn't include the physics engine. We'll get this. Because physics engine used to be a homework assignment in the course, and I would phase it in and out. I'd run it every once in a while, every few semesters or so. I decided to retire that assignment. I'm not going to use physics engine again for a variety of reasons. So today I uploaded Jumper with the physics engine. So we can check out this game. If you go to View and Jumper app and run this, we can play the full game with physics now. So this is what we want to talk about today. It uses the state pattern. The state pattern is what we want to talk about, of course. But I want to introduce what the game is, and it's a jumper game. You jump. That's what you do. Excuse me. So we have a two-player game. The blue player uses WASD, and then the red player uses the arrow keys. And your goal is to jump up this infinitely spawning series of platforms faster than the other player. So the blue player reached the bottom of the screen, so I get player 1 fell, player 2 would win this game. If I were to build this out a little more, it would say player 2 wins, and then restart the game, things like that. I don't want the game to stop because usually when I'm testing this, I'm just using one player and just making sure I can jump up these platforms. Make sure everything's working the way I want it to. So that's what we want to talk about today, how this is built. Oh. I hate these rooms, can I just get these clocks saying the right time? Would be nice. Is there another one that one's at least currently the right time? But I'll wait till 2:05 for that. Let me talk about physics just very briefly. So the physics engine, I alluded to this multiple times throughout the semester. I said there used to be this physics engine. Just imagine we have a physics engine at various points. We were talking about inheritance. The way this physics engine works, I won't get into the details. The code's there for you if you're interested in exactly how it works. But where inheritance is used is through this update world method. This is the only public API method of the physics engine. Everything else in this is internal to the physics engine, and using the engine, we don't care about any of the internals. Update world is the one method that we use, that we'll call, and it takes a reference to a world object, and the amount of time that's passed since the last update. And then the physics engine will go through this world object, which has two lists, static objects and dynamic objects, and then updates all the physics of all these objects. Dynamic objects should have physics applied to them. They are allowed to move around in the world. If they have velocity, they should advance based on that velocity. If they're in the air, they should fall due to gravity. Static objects don't have physics applied to them, but they can still have collisions applied to them. So the physics engine will detect collisions between dynamic and static objects. For our purposes, we have platforms and walls, which are static objects, and then the players, which are dynamic objects. So we want to know when a player collides with a platform or a wall. So that's how the physics engine works. And then whenever we want to apply physics to something, we would extend dynamic object and then build out any other functionality that we want. Then we throw all those dynamic objects, which will be our two players in our example, into this game world, and then let the physics engine do its thing. So that's all I want to talk about the physics engine. Everything else is internal to that. I'd be happy to talk about anything else with this project. If you're curious, come to office hours and ask about it. I'd love to spend lots of time talking about how it's designed and everything, how it works. But for our purposes today, I just want to talk about how I applied the state pattern during this code. It's 2:06. That's fine. Let's do this. Today I want to get the lecture question out of the way early. It's one of the rare times where I'll do it at the beginning of lecture. as opposed to at the end. So let's get this out of the way. It's obviously a freebie. And then we can just sit back and talk about this, the architecture of this jumper game. Anyone need more time? Everyone got this? Okay. Everyone good? All right. Done with that. I'm going to cue this up for 312 while I'm here before I forget. I don't want to accidentally give 312 a freebie. All right. Oops, wrong one. I did switch those, didn't I? All right, so I did upload slides. If you don't see the link here, just refresh the page. I uploaded these today. Let's get these slides and talk about how this design works. The state pattern. So one more example of the state pattern, of course. So this is the game we want to build. We have 2 players that can jump up infinitely spawning platforms. You can test me on that. The code will just go on forever. I guess until you run out of memory would be when it would stop. And your goal is to climb faster than the other player. The inputs to this, the way users play, they only get 3 buttons to play with: left, right, and jump. For player 1, it's A, D, and W. So it's WASD controls, but we don't use S for anything. And then the arrows, it's up, left, and right. We don't use the down arrow for anything. So those are the inputs. That's the only thing users get to do, is press those 3 buttons. And we want to build all the functionality of the game built around that, when we only get 3 user inputs, 3 different user inputs. So that's what we want to build. And of course, we're going to use states, and that's the good stuff that we want to talk about today. So here's my spec sheet. This is what I want to build into this game. And for a platformer game, platformers are, I'll say surprisingly, maybe not surprisingly if you're familiar, but platformers have surprisingly complicated mechanics to jumping. If you're playing a platformer game, the core mechanic that you have is running and jumping, just moving around in the world and moving around through the air in this world. So there can be really complex behaviors there. And this game is no exception. Of course, it's not going to be overly complex because it's a lecture example. But it will be definitely more complex than any other state pattern or any other example that I've shown in this class at all. So we have fairly complex behavior. To get a jump to feel pretty good, and you can argue with me and disagree if you want, but I think the jump feels pretty good in this game. To get it to feel good, there's actually some complex logic that has to go into that to get that feel. You can't just say, like the first 2 bullet points here, when the left or right keys are pressed, we're going to walk left or right, and when the jump button is pressed, you're going to jump. You can leave it like that, but the game's not going to feel great. You've probably played, if you've played games, if you've played platformers, you've probably played one that doesn't feel great. It's because they just leave it at that. Like you hit the jump button, and it goes through a jump, and you have no control throughout the whole thing. We want more complex behavior than that. So let's go through the rest of these bullet points, the more complex. Starting at bullet point 3, we get a little bit more complex behavior. If I'm walking in the game and I jump, I should jump higher than if I'm just standing still and I jump. So a little bit different behavior depending on whether I'm walking or standing still. I should jump at different heights depending on how long the player holds the jump button. So if the jump button is pressed and held throughout the entire jump, we would call that one full big jump. You're going to jump at your maximum height. If you just tap the jump button, it should just be a little hop. And if you hold it down, anything in between there, you should have some medium jumps. So the user should be able to control how high they jump based on how long they hold the jump button. And for the challenge of the game, this is the big one of how to time your jumps to be able to make sure, like, your goal here is to jump just high enough to reach the platform that you're targeting and no higher than that. So you have this risk-reward payoff. If you're playing this game against somebody else, trying to jump as fast as you can, you want to just barely jump high enough to reach your target platform, so you land right away and then you can jump right again right after that. So if you land just barely on the platform, you can jump again and climb pretty quick. If you hold the jump button a little too long, you're going to waste a little bit of time. If you hold the jump button a little not long enough, just barely not long enough, you fall through the platform, you miss completely, and you have a really high risk involved with that. So that's where the challenge would come in the game. So we definitely want this feature. Without this feature, the game's not that interesting. It's not competitive at all. And you would expect this feature in your platforming games. If a platforming game doesn't have this feature, it just doesn't feel right. You would expect that feature in there. So we're going to have a feature in our game. If we change direction mid-air, we should slow down. So we will let the player change direction mid-air so they have control even when they're in the air of their jump. But if they're running and then jumping and they turn back around mid-air, they're going to lose some of their velocity. We should jump through platforms when jumping up, but land on platforms when falling down. For most of that, the physics engine is going to take care of it for us. So we're not going to see that in our state pattern directly, but the physics engine is going to handle landing a collision with the top of a platform while moving down versus a collision with the bottom of a platform moving up. One of them, the physics engine is going to ignore. I say physics engine, but the platform class is going to ignore, which extends static object, which is collisions are controlled by the physics engine. And then falling down, we're going to handle that collision and notify the player object. If you walk off a ledge, you should fall off it. So if this player walks off this ledge, they should fall down. You would expect this behavior, but it would be easy behavior to forget about and have a bug in your game where if somebody's walking along this ledge, it'd be easy to have them just walk on error over here. If you just miss a little bit of logic in your code, that might end up being the case. So we want to make sure we explicitly say if you walk off a ledge, you're going to fall. And then finally, when you reach the bottom of the screen, we're going to block all inputs. So once a player reaches the bottom and loses, it's not that they just fell off the screen. Like, they can't jump back up and catch up. All their inputs are blocked, and they can't do anything after that point. No user input should register anything. Here we have an object contained main var new player player class lets us. If I'm understanding your question, the height variable would only go on the heap, not on the stack, but the player name is a constructor parameter, so it will go on the stack and heap. Assuming var height int 9 equals 9, assuming that's not in the constructor, that's outside of all the methods in that land where it becomes a state variable, that would not go in the stack frame in our memory diagrams. So that's all the functionality we want. And of course, we can add more functionality to this. We might play this and then realize that there's something else that we want. But this would be the start of our functionality for this. And we want to use states. So we don't have to use states. And again, your decision whether or not to use the state pattern, that's up to you as a developer, whether you think the state pattern will be beneficial or not. I'm showing you what the state pattern is. I'm forcing you to use it on homework 2 and giving you practice using it. After homework 2, and for the rest of your career, likely nobody else is going to force you to use the state pattern. So it's up to you as a developer to say, okay, that state pattern thing, I see that this can be beneficial in certain applications. There are certain situations, certain problems that you face in coding where the state pattern might be beneficial. You might decide that's not beneficial, where somebody else might, and that's fine. It's up to you whether you're going to use the state pattern or not. So you don't have to use the state pattern for this, of course. I'm going to because I'm teaching about the state pattern. But this is a situation where I would argue that not using the state pattern, not necessarily a state pattern, but not having a well thought out architecture to your code is going to make this a nightmare to develop. If you throw all of this functionality in giant 100-line methods with all kinds of nested conditionals for each situation, this would be absolute hell to write and even worse to maintain. So and by maintain, mostly I'm talking about adding features or updating things to, updating features. But adding new features. If you build all these features in our spec sheet, you go out and play test it, you get end users get their hands on the game and they say, man, this game is almost okay, but I really feel like I should be able to run in the game, where if I'm walking in one direction for a full second, I should enter a run velocity and then be able to jump even higher. Like, I feel like this game should have that feature. You get that feedback and you sit down to code it. If your code is in giant 100-line methods or more, that's going to be hard to do. That's going to be tough. You're going to go in the middle of this 100-line method and shoehorn in this new feature, and that can get very difficult. Now, I'm not saying you necessarily have to use the state pattern, but if you don't have any mindful, well-thought-out design and architecture to your code, you just have one class with everything, that's going to be hard to do. It's going to get more and more difficult as our programs get larger and larger. This program, you can see the code in the repo. It's a pretty large program. It's not overly complicated. It's not crazy huge, but it's definitely the biggest example we've seen so far through 115 and 116. So let's apply the state pattern instead. And when we do apply the state pattern, they're just like our other examples, designing our code, developing the architecture of our code is going to take quite a bit of work. It'll come at you fast. I'll do it in a couple of slides here. But it takes a while to sit down. Like, for example, it did take me a while to sit down and design how I want to apply the state pattern, what that's going to look like. But once you have that, writing the code is almost trivial. It's super easy. If you look through the code that applies the state pattern, I don't think I have a method that's more than 2 lines. Very straightforward code after you apply the state pattern. So we're going to follow the steps that I've been talking about since we started talking about the state pattern. First, write your API. What are the methods that can be called that we're going to defer to the state for functionality? And when we write our state abstract class, those are going to be the methods in that class. So what am I going to defer to the state for? This is any method that's going to change its behavior ever. If you have a method that's going to change its behavior, it goes in the API. The only methods that you wouldn't defer to the state and put in your state API that you would put in our example, in the player class itself, would be methods that always do the same exact thing. For example, I think I don't memorize all the code, in case you can't tell, but I believe the reaching the bottom of the screen and getting a game over state, I believe that's in the player class, because no matter what, if you reach the bottom of the screen, you're done. That does the same thing every single time. I don't need to defer to the state. Like, I don't care what state I'm in. When you hit the bottom of the screen, you're done, no matter what. So that can go in the player class. That's not part of my API. Then decide what state should exist. When do we have a different set of behavior? So whenever one of those API methods changes its behavior, that's a new state. So I got to pick apart any situation I can be in where I have a different set of functionality in the API methods. When does at least one method do something different, have different behavior? That's a new state. And finally, deciding all my state transitions. How does the collision work for the platform? So fairly complex. I'll try to give a TLDR on this one. But if you want to talk about it like in office hours or something, I'd be happy to go through all the code. How does it detect a platform collision? So a platform is a static object. A player is a dynamic object. So the physics engine is going to detect when that collision happens. And the physics engine, the part of the homework that crushed everybody, it was the task, what would be the task 3 under the current format, or the application objective maybe, is detecting which surface the collision occurred on. So the physics engine works on rectangular prisms, so you have 6 sides, and when there is a collision, the physics engine will determine which of the 6 sides or 6 faces were collided with. So if we collide with the top face, and everything has to be orthogonal in the physics engine, when you collide with the top face of a platform, the platform class overrides the collision detection method and says, if you collided with my top face, then tell the dynamic object that you've landed on a platform. But if the collision is with the bottom of the platform, don't do anything. So the physics engine handles most of that. And of course, there's a lot of vector math. That's why I don't run the homework anymore, so I finally retired it. There's a lot of physics math involved, which started tripping up students who didn't take high school physics or any class that introduces what a vector is. There were certain students at a disadvantage, so I ditched it. But if you're into physics, vectors, and all that stuff, look through the physics engine code. There's a lot of fun stuff in there. For example, when you're hitting like near the corner of a platform, determining whether it's a side collision or a top collision is tough. So if you jump exactly on the side of a platform, you should still go through the platform. You have to actually land on it to be able to get that collision. Coding that in the physics engine, that's what tripped up a lot of students. It was maybe trickier than it needed to be. Part of why I retired the assignment. So the API, like all the other APIs that we've seen, the API is pretty straightforward. It's a little more complex than the other ones, a little more that we have to think about. I actually have 6 methods. Instead of just the 3 button presses, I have the button pressed and when it's released. So I'm going to keep track of when the player is holding down the button, and then when they release it, that's going to be another API call. So I have 2 methods for each button, whether they're pressed or released, and a third method for when they land on a platform. If you land on a platform, I want to know about that because I have to handle that, especially when you're falling and you land on a platform. So it's going to be another API method because that behavior changes depending on what state you're in. And before, I got to give a disclaimer. There are a couple of conditionals in the code, in this state pattern. Don't get mad at me for that. Don't attack me for it. There are just a few situations where we kind of have to use conditionals. For example, the big one that I don't know how to get rid of is when you reach the apex of a jump. I need to know when the apex is reached. I need to know when the apex is reached so I can transition. Well, we'll get to the states, but I need to know when the apex is reached. And I don't know how to do that without a conditional to say if the z velocity in the physics engine, z is going to be the vertical axis. I want to know when your z velocity goes from positive to negative. At that moment, I know I hit the apex. Can't do that without a conditional. It's one of the things that makes this unsuitable for a homework assignment because I can't ban conditionals and then say, well, there's this one situation where you need a conditional. I can't do that. Yeah.
Yeah, I have a question. So would going from one side and exit to the other be hard to implement, or is that something that
Sorry, go from one side to the...
let's say if you go through this
left and right?
Yeah. So if you jump to the left, all the way to the left, and you want, right, some games do that.
Like the wraparound? No, I don't allow that. So when I go to the edge, it's hard to see, but both edges have a wall on there with collision detection as well. So when I go up against the right or left, it's just going to stop me. So I don't have screen wrap. I guess I could have implemented this with screen wrap. It would have been interesting. But no, I just don't let players go outside the bounds of the level. Maybe I should have screen wrap. It wouldn't be hard to do. Instead of the collision, I would just change their X position to wrap around. And since I talked about axes, the left and right is the X axis, and then Y would be coming out of the screen. So Y axis isn't used, and we're looking at an XZ axis with positive Z going up. That bugs some physicists. So if you're really into physics and that bugs you, I'm not sorry, but that is the way it is in this game. A lot of game engines do use that. I didn't change that just to be... Wait, did I even change it? I guess the only difference is you usually think of Y as being up. But oh, I know what bugged the physicist. I have a constant for gravity, and that constant is a positive value. That's what bugged them. That was the one. But gravity is positive 9.81 in my code. And they hated that. And when it was a homework assignment, I said, your gravity has to be positive, deal with it. And then you had to negate it in your physics engine. That and the y-axis were the two things that really bugged people. But that is pretty standard. Like modern, I believe, I'm going to forget which one it is. I'm going to say the wrong one. But I think Unity uses the same axis system, and its constant for gravity is positive. Like I didn't just make that up and change it just to be annoying. It's common in computer science. Anyway, so the API, I already talked about those. Let's move on. And then picking out the states. So far, picking out states hasn't been that hard. With the TV, on, off, mute, you can look at the spec sheet and the states just jump right out at you. You don't have to do too much work to find them out. It's not overly complex with Jumper, but I think it's definitely more complex than the TV to pick out what states you should have. When does your behavior change? I think it's about as complex as the self-checkout on the homework. Maybe a little easier, maybe a little harder. I don't know, it's hard to tell. I don't think the self-checkout states are too hard, but I've been thinking about that assignment for years, and I'm a little tainted by just seeing it so often that the states jump out at me. I don't know how clear that is. But anyway, we look at what states we can be in. If we're walking, or if we're standing, is going to be our first state, and then we press left or right, we're going to enter a walking state, and the jump button is going to have different behavior whether we're walking or standing. So if I have to jump higher when I'm walking versus when I'm standing, an API method that does something different, those are two different states. When I hit the jump button and I release the jump button, that jump release method is going to do something different whether I'm in the air or on the ground, and the jump button itself is going to do something different when I'm in the air. So jumping is definitely a different state, which I'm going to call the rising state. And also when I'm in the air changing directions, that API method is going to change behavior. And when I fall down, I'm going to land on a platform, versus when I'm jumping up, I'm going to jump through a platform. So I have different behavior whether I'm falling down or rising up. So whether I'm jumping up and then I hit the apex and I'm falling down, that's going to be different behavior. I'm going to have a state transition right there, which is probably the hardest state transition to see, the hardest different state to tell. And finally, the dead state. You fall below the edge of the screen, disable all your inputs. That's different behavior. Every API method just changes behavior to do nothing at all. So that state is going to be, that's going to be a different state as well. And finally, our state transitions. So we look at, again, through our spec sheet, do a third pass, and say, okay, when do I change between two of these states? If we're standing and we press left or right, we're going to transition to walking. If we're walking and we release left or right, we're going to transition back to standing. If we're walking or standing and we hit the jump button, we're going to transition to jumping. If we're falling and we land on a platform, we're going to transition to standing. And for what it's worth, in my code, if you land on a platform and you're holding left or right, you will very briefly transition to the standing state and then transition to the walking state. for one frame, you'll be in the standing state. So just for what it's worth, anybody who's interested in that, you will transition only to the standing state when you land on a platform, and then immediately transition to a walking state if you're holding left or right. And if you're walking and you walk off a platform, we want to make sure that we get this feature. You're going to go to the falling state. You're jumping and reach the apex of your jump. Hit the falling state. This is the one, I say one, but I have a sprinkle of conditionals throughout the code. Go into the falling state. And then from any of these states, you reach the bottom of the screen, transition to game over. So these are all my state transitions, and I like to visualize that. So we want to look at our state diagram and be able to visualize what all our states are, what all our state transitions are. Our initial state will be the standing state. We jump, we go to rising, we reach the apex, go to falling, we land on a platform, go to standing, press left or right, release left or right, walk off a platform, or if we press jump and my label on this arrow got destroyed at some point, walking and press jump, we're going to go to the rising state. And from any state, I didn't want to clutter up my diagram with arrows from every single state over to game over. So if we're in any state, we'll transition to game over if we reach the bottom of the screen. Doesn't matter what state we're in, every state's going to have the same behavior of going into the game over state. And at this point, things get pretty easy. So the hard part is designing, getting to this point. What are my states? What are my state transitions? What are my API methods? But once you have all that down, now it's just like we saw in the other examples. Your task is now going to each one of these states and implementing each of the API methods. When I'm in this state and this API method is called, what should we do? When we're in the standing state and the jump button is pressed, what should we do? The way the physics engine works is I'm going to set the velocity of my player whenever the player should move. So for this, when I'm standing and I press the jump button, what I'm going to do is set the z velocity to whatever their standing jump velocity should be, set their z velocity to that, and then have a state transition to rising. Then the physics engine does the rest. I offload a lot of work to the physics engine. I'm just going to set velocity and then move on. So standing, and I press the jump button, set the player's z velocity to some positive value for their standing jump, however high I want them to jump when they jump from a standstill, and then transition to the rising state. 2 lines of code. I'm standing and left or right is pressed. I'm going to update the x velocity of the player and have a state transition. 2 lines of code. Set velocity, state transition. Walking, and I hit the jump button. I'm going to set the z velocity to a positive value, which will be higher than the standing velocity, whatever the walking jump velocity should be, and then a state transition. 2 lines of code. I reach the apex while I'm jumping, state transition, 1 line of code. Each one of these methods is going to be almost trivial to write. Once you get to this point, like if I gave you a homework assignment where I set up the whole state pattern for you, like for self-checkout, I said, here are your states, here's your API, here's your state diagram, implement each method. You'd laugh at how easy it is, because implementing each method is trivial. It's easy. I guess for self-checkout, it's a little bit more complex, but not overly so. Like you shouldn't have a 10-line method anywhere in your self-checkout code in the state pattern, in the states themselves. Actually, probably throughout the whole assignment, right? Where would you ever use 10 lines for a single method in that homework? So once we have this, things get easy. We just implement these things. I'm going to make it more complex because if it were that easy, then what else do I talk about the rest of the lecture? So I'm going to make it a little more complex so I can talk about some other topics. Actually, I should stop for questions. Anybody have questions at this point? This lecture's kind of a lot, but you're also getting pretty familiar with the state pattern, I think. But there are questions. I want them. I want those questions. Okay, let's make it more complex then. There are no questions. So what we could do and what we have done in the past with the state pattern is create one state abstract class. And by the way, I used a little bit different notation here, but this is my inheritance structure. This is my class hierarchy, my type hierarchy, whatever word you want to use to describe it. So the arrows mean inheritance. Standing extends on ground extends state. So we could just have our state abstract class and then extend that for each of our 5 states. That's what we've done in the past. That's what you really should do on your homework, unless you want to add the complexity. If you're comfortable with all this stuff, that's fine. But that's really what you need to do, is get each of these 5 states extending the state abstract class. But I'm making an observation here, which is the very first observation we made when I first introduced inheritance, is that the standing and walking classes and the rising and falling classes, these states have a lot of common functionality. And I don't want to cut and paste this code between these states. A lot of their methods just do exactly the same thing as the other one. So my standing and walking state, I'm going to factor out all of that common functionality, all those common behavior, all the common methods, and factor it out into an on-ground state, which will have all of the common methods between the two. And then these methods will just override whatever's left. Whatever's different between standing and walking, those are the only things that should go in the standing and walking class. This was the same thing when we first started talking about health potion and dodgeball, where we observed that they had common functionality. We factored that out into one common abstract class and then extended it in both of them. We're taking advantage of that idea in the middle of our state pattern. Instead of having all 5 extend state directly, let's factor out the common functionality and build these intermediate states. These will still be abstract, will never be in the on-ground state. It's not a state in our state pattern, but we're using this to cut down our code duplication. Whenever I see the same code twice in 2 different places in my code, in my projects, I'm thinking that there's a better way to do things. In this case, if I see the same methods in standing and walking, I'm factoring those out into a common method, putting that common code here, and then extending them both here. And then when I do have a running state, I want to have like a speed run state when I'm walking for a while and then I start running, or I'm holding a run button maybe, and I have this running state, I'm just going to extend on ground and just change what the x velocity is, and maybe the jump height will be even higher when I'm running as opposed to walking. Those are the only 2 things that change. Those are the only 2 things that I want in that class. Everything else will be in the common on-ground method, on-ground class. Same thing with rising and falling. They're both in the air. They have a lot of common functionality just by the nature that they're both in the air. So I'm going to put all that common functionality in the in-air class. Then those will, of course, extend state, which is just defining my API. So we implement everything in the state pattern, we get it out there, or we implement everything in the game, I should say. We release it, our play testers get their hands on it, they're like, this game's okay, but really needs a double jump. And we're not using the state pattern, and we have a couple of methods that are each 100 lines of code. We got everything crammed into one player class, and we go, how are we going to add a double jump here? We try to jam it in the middle of these giant methods. We add some state variables for your double jump. Those of you not familiar with double jump, it's while you're in the air, you can jump one more time and only one more time. So there's a lot of testing, a lot of potential bugs here, making sure that the player doesn't get infinite double jumps, and making sure that when they land on a platform that they reset their double jump. Once they land and jump again, they do get another double jump. So we want to make sure we have all this behavior. In our double jump, shoehorning that into messy code with large methods is going to be difficult. You might have to rewrite your entire program. You might have to go back to the drawing board and design something better. And then after you implement that feature, you have to check all of the other features that you broke in the meantime. You run your other tests, and you realize that some tests that were passing are now failing because when you edited code in the middle of a giant method, you broke a whole bunch of other stuff. You go through a bunch of debug cycles, fix all those features, You finally get this feature rolled out after much agony and pain. You go back to your play testers and they go, never mind, I don't want to double jump. I didn't like that. And then you go back to where you were. With our state pattern, or with any mindful architecture, it doesn't necessarily have to be the state pattern, but with mindful architecture, a well thought out structure of your program, this is going to be no big deal at all. We can add this double jump in almost no time, with almost no pain. So what will change in our state pattern is we're going to edit the rising and falling states to enable the jump button. Before, the jump button just wouldn't do anything in these states. You don't want to jump while you're jumping. But now with the double jump, we're going to let the jump button actually just jump. So the jump button is going to set the Z velocity to some double jump velocity, however high we want our double jump to be. I believe I set it to the standing jump velocity, so you don't get a big jump for your double jump, but you get a good sized jump. And then after you jump, we need to shut off the double jump functionality. We want to make sure you only get one jump. So we're going to transition into new states, rising after double jump and falling after double jump. These methods, these states will be identical to rising and falling states, except we're going to disable the jump button. So for these states, we can extend rising and falling and just override jump press to do nothing. That's the only change, that's the only difference in behavior. So we extend those classes and just disable the jump button. Then we have a few more state transitions. This shouldn't say respective. This should say if you're rising or falling and you hit the jump button, you're going to transition into rising after double jump. There won't be a respective after double jump state. It'll always be the rising after double jump. Once you hit the double jump, the jump button to double jump, you're always going to be rising. You're not going to hit that button and be falling. It doesn't make sense. So we're going to transition to the rising after double jump. And when we hit the apex, we're going to transition to falling after double jump and not falling. This would be a common bug to make, an easy mistake to make, is transition from rising after double jump to falling. So we do have one extra method to override. When you hit the apex, we have to override that state transition. If we forget to do that and we transition from rising after double jump to falling, well, the falling state allows a double jump. That would give users infinite double jumps. They would jump, hit their apex, jump again, hit their apex, jump again, hit their apex, jump again. So we want to make sure we're transitioning into a state that disables the double jump. And then when we're falling after double jump and land on a platform, we go right back to the standing state, which trivially re-ables the double jump functionality. Now this is a case where I wouldn't go full hog on the state pattern. I would just do this inside my rising and falling states. I would have a flag that says, did I use the double jump? And this, I would just throw one conditional in there and shut off the double jump after I jump. And then make sure from rising to falling, make sure that I forward that flag to let falling know if the double jump was used or not. I think that would be less complex than adding new states. But for a lecture example, I'm going to add more states. And our state pattern, our state diagram gets a little more cluttered. We have these two extra states. Whether we're rising or falling and we jump, we're going to go to rising after double jump, reach the apex, falling after double jump, land on a platform, we go all the way back to standing, and trivially get our double jump back. We're standing, we jump, we're rising, we jump again, we get a double jump, and then once we land again, we get our double jump back. So through the state transitions, our state transitions take care of making sure that we get our double jump back each time we land on a platform. We also trivially get walking. I walk off a platform, I still get my double jump, even if I walked off a platform and I only get one jump, we'll still call it a double jump. But if you walk off a platform and you jump, you still get that double jump functionality. And our type hierarchy expands a little bit, rising after double jump and falling after double jump, extend rising and falling respectively, and then just change the methods that we need. Disable the jump button, and for rising, override the apex reached to make sure that we're transitioning to falling after double jump. Would there be easily a way to add more midair jumps without adding another pair of states? Yeah, that's where I would do this. I would have this be a counter and then check if I have more jumps left. then jump and decrement. It's a case where I would mix conditionals and the state pattern. Like for the homework, I have to ban conditionals to make sure that you use the state pattern. Because if I don't ban conditionals, if in lecture I'm like, this is the state pattern, I recommend it for your homework, it makes these things easier and stuff, almost somewhere between 0 and 1 of you will actually use the state pattern. All of you will just use conditionals, like you won't use the state pattern. So banning conditionals is just my way of forcing you to use the state pattern to get some practice with it, get familiar with it, and just understand what it even is. In the real world, mixing conditionals and your state pattern is definitely recommended. So instead of adding a pair of states here, just adding one conditional and a flag can make your life a lot easier. So now that we know the functionality of this, we can see all that functionality built in. If I'm standing and jumping, I jump this high. This is a full big jump. I'm holding down the button the whole time. If I just tap it, I can jump a lot lower. If I hold it a little bit, I can control the size of my jump with a lot of granularity. If I'm walking and do a full big jump, I'm going to jump much higher. Oh, I want to get this on screen. I'm also printing out all my state transitions if you want to check my state transitions here. And if I want to reach that platform way up there, I can try to reach it with a double jump. Oh, I don't quite get there. But I can use my double jump. If I'm walking and fall off a platform, I still get my double jump, so I'm giving the player a chance to get back. If they make a mistake, they can use their double jump to correct that mistake. And if I reach the bottom of the screen, disable all of my inputs, and I reach the game over state. So I don't really have time to click through all the code, which that's usually where I lose a class anyway when I start clicking through a bunch of code, so I think it's fine that we don't get to that. Feel free to go through the repo and take a look at everything there. With that, have a great day. I'll see you all Friday.